our next class, we have some graduate students and postdocs, and depending on space, maybe I'll fill in a little bit myself, coming to tell from the graphics group to tell you a bit about what they're up to. Certainly I'll strong arm some of my students in doing it, which means you may have a geometry-heavy research talk. And I know at least one or two from the vision group will come as well to share what computer graphics research looks like these days, and what are the open problems and the things people think about. It's also a great opportunity to get to know people in case you're interested in Europe, all that good stuff. These are all questions that I get in this course. Then the class after that is your final presentations, I think. Yeah? So that'll be a week from today. Oh boy. Yeah, get your eyes together. And then after that, then we're done. Yeah. So we're almost there. So almost toward winter break and snow and frozen and all that good stuff. Okay. Right. So today we'll talk about output devices, which is sort of. Remember that this whole class is organized roughly like the graphics pipeline, right? We started with control points and curves and sort of some abstract data representation in terms of shape. And then we saw that our control points and curves are also relevant toward animation, which is a different type of data we need in graphics. Then we moved on to two different rendering algorithms, right? Ray tracing, rasterization. And finally, all the way at the end of the graphics pipeline is, like, to me, the least interesting part, because I'm a theory guy, which is the thing that actually sends photons into your eye, and those are the output devices. Of course, while I like to kvetch about the fact that I don't like talking about this stuff, the reality is that we wouldn't have computer graphics as a discipline without output devices, so it's certainly worth covering roughly what goes on in these things. Although, of course, this too changes day to day. And in fact, especially now, in a sense, the way that we interact with computer graphics technology is really evolving at a really rapid rate. I mean, nowadays, just looking at many of you in front of me, rather than paying attention to class, are all looking at these laptop screens in your phones, both of which are relatively new display technologies and ones that are improving by the minute. Yep. I assume that you're all doing this in the interest of scientific exploration. Okay, so our rough plan for today is to talk about 2D displays, like your laptop screen and your phone, all that good stuff, and then talk a little bit about 3D displays, which I think are currently a little on the out. Like we don't see too many, holograph, whatever, 3D glasses, other than this third bullet, which is virtual and augmented reality, which are extremely popular today, especially now that your mobile devices often have means of sensing depth. Right? The difference between virtual and augmented reality being a little fuzzy, but roughly augmented reality would be like some amount of photons coming in from the real world and some amount coming in from your screen. That definition used to be true. In fact, my very first computer graphics job was in the Naval Research Lab working on AR glasses in the 90s. You can guess how well those work. But that aside, nowadays augmented reality actually is, the pixels pass through and into your eye in a funny way, right? They go into your phone camera, through the phone's processor, and then the phone emits photons that are the same as what's on the other side of the phone. Which, if you think about it, is weirdly wasteful, but probably makes a lot of sense. But of course, in the process of doing that, it's augmented and enhanced in different ways. And I think that's probably the technology that you guys, in the next, 2 or 3 years, will see evolve quite a bit. Okay. But of course, probably the primary display that we all see day in, day out are 2D displays. And there are many different types out there. So roughly, again, the way that we've organized this class, right, is mostly sitting up here in the graphics pipeline, which is the sort of software part of the graphics stack. But it really is a stack, and hopefully many of you guys have heard this terminology before when we talk about a software stack. The basic idea here is that there are many different levels of abstraction that might be useful in writing a piece of graphics software. Right, so all the way up top are tools like Unity that help you with displaying a scene and storing data and all that good stuff. Most of our class has been kind of one layer down where we're talking about rendering, and of course in many graphics libraries that's actually kind of taken care of for you, right? Like you're talking about materials and art rather than how a pixel is shaded on the screen. But of course sitting underneath DirectX, OpenGL, those are basically the only two major options these days, except for maybe for dedicated hardware. There's all kinds of different layers that happen, right? there's the kind of kernel space, which has to do with your operating system, your device drivers. If you guys take OS class, then good luck with that. It's never my favorite. And then all the way at the bottom, of course, is your graphics card and your chipset. And I think something that we've learned in this class, one of the kind of unique things about graphics programming is that it happens on both of these devices. Right? There are certain parts of graphics pipeline, like dealing with control points and splines, which actually computationally really isn't that much load. It's mostly just on the map side, getting the formulas right. And then on the other hand, things like rendering and so on involve this massive amount of computational load, to the point where really advances in hardware were driven by computer graphics for many decades. Okay, so today we're going to sit kind of down here, at least for a little while, so you guys get some rough, abstract idea of what's going on inside of your display. And of course, there are many, many different display technologies, and we see and interact with them all day long, right? So the one that we used to cover in quite some detail in graphics class was CRT, cathode ray tube, which of course these days actually I don't see too many of. Those are like the big computer monitors that you used to see where there's space between your screen and stuff behind it. Nowadays, probably what's more common in your life is an LCD, like what's in front of most of the people in this class. But of course, there are many other options, including DLP, which are projector technology, and even some displays you might not think about, like the screen of your Kindle, which is sort of passive, right? We'll talk about that just a tiny bit. But of course, I can't help but talk about CRT a little bit, because that's the display I'm used to. CRTs and many other displays are all built on this idea of phosphorescence, right? Where essentially you have a piece of material which absorbs some energy and then slowly releases that energy as light. This would be different from a mirror, which takes in energy and immediately bounces it right back off as light. We'll see that also shows up in DLP technology, right? But a phosphorescent material, you zap it with some energy and then it stays glowing for a little while. Why do you think that's pretty important for a lot of display technology? Remember that your graphics card actually doesn't just display an image all the time, right? Once, 30 times a second, it renders a bunch of pixels and sends them out to the GPU, and it just keeps doing that on repeat. Yeah. So what happens in between? Well, the answer is not very much from your hardware's perspective, right? It sends that signal out, and now it's your hardware's job to display it, right? And what would be a bad thing is if for 1/60th of a second it showed that image and I want to make it, right? Because then your screen would look awfully dim, or it might even give you a seizure if you're really lucky. So the reality is that these phosphorescent style displays are totally reasonable for a computer screen, because you put the image up on the screen and it persists for just a little second while you're preparing the next frame, and that's sort of what gets relied upon in some of these old CRTs. Yeah. So your CRT display is one of the more simple ones to explain and understand. Roughly, there's a vacuum tube inside of your screen and a gun all the way in the back. This is the non-violent kind of gun that emits electrons. And essentially, as your video signal goes through the CRT, this modulates where the electrons get sent. When they kind of, it's like Speed Racer, they like get shot out of this gun and toward your screen. Electrons are negative, your screen has some positive, so they want to go toward it. They run into the screen, and then what's sitting on the screen is a phosphorescent material that lights up. Yeah, and that's what's going on inside of your CRT. Of course, typically CRTs are really secretly maybe black and white, and then there's some fixed pattern of color that happens on there. And there's also a fixed pattern of where the pixels are, right? Because oftentimes, rather than displaying all the pixels at once, what's really going on is like you're just scattering electrons back and forth, back and forth. And that pattern where you scatter is called the raster, which might sound familiar given the algorithms that we talked about for rendering. So you can actually see that in some old experiments. Do not do this experiment with your laptop, but with an old TV you can. Let's see if there's some audio here. So here's an old CRT. For some reason I have it blocked with magnet. So I'm going to wave the magnet around towards the screen. Take a look at that. point of putting the glass on the lab is that you're seeing the light moving the front of the TV, which probably is a technical way to do it. Okay, who wants to explain what's going on in this experiment? First of all, would this happen if I did this on your laptop? Does anybody want me to give it a try? No, it takes a pretty strong magnet too, by the way. Right? No, if you did it on your laptop, probably your laptop would no longer be a very useful laptop. But on an old TV, this is okay. For one thing, because the electronics for the TV are really in the back, right? And they're doing it in the front. But what happens here? I mean, the TV doesn't just crap out, but instead, the signal actually moves along the screen, which might be a little surprising, because somehow that doesn't feel very digital, right? That's not a binary thing, like turning pixels on and off. It worked. Why did it work? So what's generating the image on a CRT? Yeah.
Electrons hitting.
Yeah, and what do electrons do with magnets? They move toward them or away from them, depending on what pole, yeah? And so essentially, what's going on in this experiment is as they move around the magnet on the surface of the screen itself is the same. The phosphorescent stuff is staying in the same place. The raster is still the same grid. What's going on is that these electrons, which are shooting from the back of the screen to the front, are getting redirected by the magnet and then hitting into the wrong pixel on the front of the screen. Yeah, and that's what you're seeing now. So anyway, it's a nice experiment to kind of show what's going on inside of your CRT. Don't do this at home. Even if you have a CRT, like who knows what technology is sitting underneath that piece of glass. Okay, so that was the original display technology. It was perfectly fine for my generation, but these days we don't do that anymore. We have many other options, many of which are better quality. Right? As you can imagine, it's pretty tricky to engineer a CRT that's extremely high resolution, right? Like think about you're like kind of hitting a golf ball from the back of your TV and trying to hit a raster in the front, and the smaller you make those pixels, the more accurate you gotta be. Yeah. So these days, a more common technology, which is what really is in your laptops, is something called a liquid crystal display, LCD. These have to do with polarizing light. Has any of you guys ever tried to use your laptop while wearing sunglasses? No? I encourage you to give it a try. And if that works, then tilt your head 90 degrees and see if it still does. Right? So remember that light acts like a wave, and waves sit in planes. And essentially, that's the basic physical phenomenon that's being leveraged inside of your LCD. Right? So the basic idea is they make use of a very particular type of material called a twisted pneumatic. To be honest, I have the slightest idea of what's going on physically with these things, but they're pretty amazing. In that when you apply electricity to a twisted pneumatic, an electric field rather, what happens to it? It untwists. Yeah? So it goes from this configuration to that one. Yeah? So why does that matter? So we take light, which is in your LCD screen is really, so there's like another layer behind here, which is like a light bulb. Yeah? Have you guys experienced this? Like so every once in a while when you have an old laptop, the backlight dies. It's really annoying. And that's because, and it's not like just individual pixels stop working on your screen, the whole screen stops working at once. Right? And the reason is that sitting probably right here in your laptop bezel, it's basically just a light bulb. It's not intelligent at all. It doesn't know about the signal that's going through your screen, nothing. It's just a source of photons. Yeah? Those things get reflected through the back. By the way, it's a bright one, right? Because you can't put it behind the screen, so it's covering the whole thing. Yeah? These things go through a polarizer, which makes sure that the light waves are all moving inside of a single plane, instead of the usual chaos that happens behind there. And then what's going on inside of the twisted pneumatic is that it itself is its own polarizing filter that's aligned with this material, right? And so by default, the material sits 90 degrees to the polarization that comes out of the filter on your screen, right? And in effect, if you think about it, that's like putting a shade in front of the light, right? Because the light is polarized this way, I have essentially a slit that's facing the other way, and the light can't fit through. Not physicist, this is a very abstract picture. And then when you activate this object, what happens? Well, suddenly now you have space for the wave to go through, and the pixel gets lit up. Yep. Once again, your pixels are still on these tiny patterns of RGB. This is not a color phenomenon. This is just turning on and off pixels. You guys see that? So that's the basic trick behind the LCD screen. The real magic that takes place, I encourage you guys, if you like this kind of stuff, take an electronics class, is the fact that like your screen is too small to put circuitry back here on the back of the actual display, right? Especially because if you did, well, it would probably block that light that you're trying to display, right? So instead, the magic is that there's circuits sitting on the side and on the top of your screen, or maybe bottom, I don't know. Where essentially what happens is you target a pixel by putting electricity in the sort of horizontal and vertical line, and that's the thing that controls the pneumatic that happens right at the intersection of those. Yeah? As you guys are going to see, in all these display technologies, at least for like a theorist like me, they're like just this total magic ballet that has to happen for these to work, right? I mean, they all have to happen in the same clock cycle in order to synchronize like what pixel am I controlling, and how does that, you know, interact with the AC current that's going into my computer, and all these things matter in a really terrifying way. I found a nice video that explains a little bit more deeply what's going on inside this LCD. But let them do it. Okay. And it's got some too.
If you were to zoom in on the monitor you are using to watch this video, you would see thousands of small red, green, and blue dots. 3 of these grouped together make up one picture element, or pixel for short. When you split up each pixel, you will see a backlight, 3 color filters, and polarizers. As light leaves the backlight, it travels along different planes, including the horizontal and vertical planes. The first polarizer only allows light traveling along the horizontal plane to pass through it, and on to the color filters. With another polarizer that only allows light to pass along the vertical axis, all the horizontal light waves are blocked, so no light reaches the color filters. This is where the liquid crystals come into play. If you were to look closely at one of these liquid crystals, you would see a transparent electrode on the front and the back, as well as etched glass on the front and the back. Liquid crystals typically orient themselves in random directions until the horizontally etched glass in the rear and the vertically etched glass in the front force them to twist into a predictable pattern. As light passes through the compressed liquid crystal, it naturally follows the path of the molecules, so that any light traveling along the horizontal plane exits along the vertical plane. By reintroducing the electrodes and passing electricity through them, we can get the molecules to align themselves in the direction of the electric flow, causing light to no longer twist when passing through the liquid crystal. When we place these crystals back into the pixel, we can see that the light from the backlight will pass through the horizontal filter, get twisted into a vertical position by the liquid crystals, and then flow through the vertical polarizer to the color filters. However, if we turn on the electrodes, then the light is no longer twisted by the liquid crystals and stops at the vertical polarizer. By adjusting the amount of electricity that flows through each set of electrodes, we can control how much light reaches each color filter, and therefore what color is seen on the display. We generally talk about colors on a display in terms of how bright the red, green, and blue are in each pixel, from 0 to...
That's right. So now you guys can see there's just a totally amazing feat of materials and electronics that goes into it. Which is really the takeaway today. Of course, there are many different types of LCDs out there, which you might not realize that, like the face of your clock, well, the face of my clock, maybe yours. I think you've all seen the displays that look like these. Here's one here. These are also LCD displays, but rather than emitting light, what's going on is they're just using light that comes in from the outside, is reflected off the back, and then comes back out. Right? But it's exactly the same phenomenon. And color here, again, is pretty boring. It's just a filter sitting on top of your screen. Okay. But if you remember, actually, it is important to remember how color gets displayed in your screen, right? Because in all of the code that we've written in this class, our basic abstraction has been that red, green, and blue sit at the same place, right? Like when you wrote your rendering, your ray tracer, essentially you made a big n by 3 array of colors, but the reality is that's not how your screen works, right? In fact, the red, the green, and blue are slightly offset from one another. And if you really want to get just that tiny additional amount of precision, you might control those 3 channels slightly differently to account for that offset. Right? And again, where do you guys think that matters for rendering? In your like what rendering tools typically make use of subpixel anti-aliasing? Sometimes fonts have these tiny, tiny ligaments that connect each other. There's millions of them on your screen, and so getting that tiny amount of accuracy really matters. So this was this idea called ClearType. As far as I know, even on these super high-resolution laptop screens, ClearType is still a thing. I don't know. One of you guys can look it up. These things change every time you get a new operating system. Right, so continuing our list of display technologies, of course, if you go to a football field, then probably making an LCD of that size is quite a challenge, right? Because it has to be lit in such a way that the backlight reaches all the pixels in a kind of even fashion. My bet is that it's a very difficult thing to engineer. So instead, we transitioned to displays that look good from a distance, but of course, if you get more up into their business, it looks closer to what you see on the left-hand side. And these are LED displays. I think from an electronic standpoint, these are sort of the easiest ones to understand. Basically, there's just a tiny light bulb at every pixel location, and you can turn it on and off. The nice thing being that you basically make an arbitrarily big display this way, because every single pixel is its own light source, right? You're not relying on a backlight to light your screen. No. Sort of related to that are plasma TVs, where also every pixel is its own lamp, but kind of on a miniature scale. So here you have a bunch of cells on your screen that are filled with noble gases that all get excited, like a little neon light bulb that gets excited when you put voltage in there. And that's what creates this image. So again, I thought I'd show just a short video where they can probably explain, zoom in.
The answer is the plasma. Each subpixel is filled with a mixture of gas, xenon and neon. When an electrical impulse of about 300 volts rushes through a subpixel on its way to the electrodes, electrons from the gas mixture are violently torn off and suddenly float freely. That drastically changes the state of the mixture. It's no longer gas. It's now plasma. It's a highly energized state of matter, but it's a state that lasts only as long as the electrical discharge. As soon as the discharge ends, the freed electrons immediately return to their places, and the plasma once again becomes gas. What's important is that as they return to their places, the electrons release their surplus energy in the form of ultraviolet rays. It's these rays that excite the subpixel, which gives off light that combines with the light given off by the two other subpixels, and together, they light up the pixel.
Okay.
Every...
I feel like I'd be friends with them. Right. So finally, kind of wrapping up our list of all these displays is one that's kind of spiritually similar to plasma, which is OLED. I think we don't see these quite as much, where you have an organic material that produces light under a certain amount of voltage. If I recall, these things are interesting largely because they can make interesting displays like this one, where you actually can, if you look carefully, you can see somebody's hands behind them. Right? So for a while, people were very excited that you can make somewhat transparent and flexible displays, but they're quite expensive to make, and they can fall apart easily. So now we go on to my favorite display technology, because I just think it's totally amazing what these things should work, which is DLP. These are used in projectors, probably the one in this classroom, and almost certainly the ones in the movie theater that you guys watch. Right, so DLP projection technology is just amazing to me. So what goes on inside of these chips is there's really just a huge array of little itty bitty mirrors. And this makes sense, because like, what are the engineering priorities when you're making your projector? Well, unlike your computer screen, the projector needs to be really bright, right? That's what has to go on. It needs to reflect a lot of light, because at the end of the day, the light is coming out of something all the way over there and landing on this screen. And I certainly don't want to like shoot a gun of electrons from here to there like we see on TV. Yeah. So instead, I prefer to send photons, because we're pretty sure this don't cause cancer. Sorry, they don't cause cancer at this particular. So what goes on here is there's a light source that's sitting inside of your projector, which is just a really bright light bulb. It's something intelligent. And then you have this DLP chip, which is sitting underneath. And the DLP chip actually has this really dense array of little itty bitty mirrors. Yeah? And so what goes on is that every mirror has two states, right? There's the state where it just sends light off to some absorber, probably like just the side of your projector. Or there's the state where it sends light out the lens and onto this screen here. And so when you use your DLP projector, this just awesome ballet of stuff happens. Right? So you have, for one thing, you have a spinning color filter that's going in front of this bright light bulb and doing RGB, 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 RGB. So there's like actual moving parts in here. There's like little elves that are shoveling light into your DLP screen. That light comes through this spinning object at just the right rate so that we know what color it is, and then it hits the DLP chip, which is controlling those itty-bitty mirrors on the chip at a rate of at least 30 frames per second as to whether or not each one is oriented toward the screen here or not. And then that pulse of light either gets directed toward the screen or just toward an absorber. Notice a lot of energy is kind of wasted, right? Like essentially there's a lot of light energy that just bounces off the mirror and hits the absorber. But it's kind of cheap because it's just coming out of a light bulb. But I hope you guys appreciate how ridiculously cool it is that somebody managed to engineer this. Because I mean, think about the synchronization that has to happen here, right? There's your computer, which is controlling this device here. This device here has a spinning object, which is determining what color is coming out. That color has to be synchronized with these mirrors, which are also synchronized with the signal that's coming out of your laptop, and then sending that out to the screen. Of course, things are really tricky, right? Because here, you can only turn a pixel on or off, so if you want grayscale, what do you have to do? Well, you have to do really crazy stuff, like modulate the fraction of times that that mirror is turned on or off. Right? So this happens at this ridiculously fast rate. I just think this is so cool. I want to take apart one of these things and look at things. But I don't think you can actually see, it's very small. Okay. Right, so that's it for kind of active displays. For an example of a passive display, like your Amazon Kindle or one of these ebooks, we can talk about e-ink. So the idea here is that when you have an ebook, what are a lot of this has to do with your engineering priorities, right? If you're going to make a book that you're reading, well, you probably don't want to have a bright light source anymore. You kind of want the opposite of that because you're trying to simulate a sheet of paper. You want very long battery life, and you probably don't want the battery life to depend on how long you're reading, because at least for people like me, I wouldn't get more than a few pages in before I ran out of battery. So instead, the kind of interesting property that these reflective displays have is that the electricity that's taken to use one of these displays has to do with the number of times you turn a page, not the number of seconds that the machine has been on. And the basic idea of e-ink is that you have little capsules with some piece of dye that can be suspended different ways depending on how you apply charge. Right? And so what happens is when you turn the page in your ebook, you flip where this stuff is, and it moves and then it just stays there. Right? So it's kind of like the combination of a clock face and then some chemical reaction. So that it just, by default now, that's what's going to be on the screen until you change it. How many of you guys have ever seen a color ebook? They do exist. Yeah, not many. And what's the reason for that? Well, the ebook doesn't have a backlight, right? That's not really how they work, right? It's taking it's just leveraging light that goes in, polarizing it, and then sending it back out, or maybe just blocking it depending on the type of ink. And if you want to have RGB, what would you have to do? Well, effectively, you'd have to filter that incoming light, which would reduce the brightness overall, right? And so it's a very hard thing to pull. Okay, so that's it for 2D displays. Now let's talk about some of the fun stuff, like 3D. Of course, it's not hard to justify why you might want a 3D display, although if you step back and think about it, you don't actually see them all that often, so it's not 100% clear that it's like the world's most critical technology to get right. I mean, I think for the last, 30, 40 years, anytime you watch a sci-fi movie, a lot of the displays are 3D, but I think we've gotten pretty far without them. So I'll be curious to see whether or not people feel like there's a lot of value in this technology or not. But of course, binocular vision and stereoscopic is very important. And the basic idea of a 3D display is that you got two eyeballs, and they need to see two different distributions of light. Yeah? But of course, doing that on a flat display is tricky for a lot of different reasons. And so in order to kind of simulate stereo, we're going to have to do one of a few things, right? Like use polarized glasses. Right? So this would be like one eye sees all the light that goes this way, one eye sees the light goes that way. And so that's one way to display two different images to your eyes. Or anaglyphs, which would be kind of like this, these things which you probably think of as retro now, where you have like one eye is blue and one eye is red. Right, but you get the basic idea of these different technologies where essentially you just want to control the light field going into the two eyes independently. Right? And that's tricky because you only got one display. Right. Of course, one of the things that's kind of cool about 3D display is that they typically don't try to accurately simulate the actual 3D experience completely. You kind of choose what you want and what you don't want. Yeah. And in particular, there are a lot of different cues in the world in terms of depth perception. And of course, as you engineer one of these displays, you have to decide which ones you want to capture and which ones you don't. Right? So some examples here. Of course, there's stereoscopic depth cues. These are the ones that involve both of your eyes. So for instance, binocular disparity, like so the difference between how your two eyes rotate to see an object. And there are also ocular depth cues, so like a single eye or both of them acting together. It's controlling angle, just the fact that you see two different images through your eyes and so on. And then finally, there are things that you can get just from a single image, right? So things like occlusion and size and shadows all control how you sense depth. And the really giant headache about making a 3D display is that they all have to agree. Yeah? And what happens if they don't? You get a headache. Yeah, it's your brain just doesn't know how to process that signal, and oftentimes it just creates discomfort. So in fact, I like, for example, I'm one of the 1 in 10 people that really doesn't like being in these 3D displays when they don't get them just right, because I really feel seasick. But fundamentally, whenever you engineer one of these displays, you're a little bit host, right? Like if I, for example, if I try to fit it on a computer screen and I have this lily pad sticking out, I simply can't display that. Because I don't have access to changing, to creating, simulating a light source that's coming from down here. Yeah? And this is this idea of a light field. How many of you guys have heard of this term before, light field? So think about this picture that we always draw when we talk about ray tracing, right? We put a little eyeball here, you have your computer screen there, and then you start drawing rays through here, right? So in some sense, you can think of your eyeball as like a little sensor that's sitting here. And what is it sensing? It's sensing all of the photons that are moving along this straight line. Yeah? So a light field is I'm going to tie my shoe while I talk. A light field is roughly a 6-dimensional function here, where the idea is for every ray that's sitting in space, there's a color associated to that ray, or an amount of light energy. Right? And you guys sort of implemented this in your ray tracer, right? So for every, you had that trace ray function, which took a position and a direction, and it gave back a color. You can think of that as a function of 6 inputs, right? Where your array is based and the direction it's pointing. Yeah? And that's this idea of a light field, that there's just sort of, in the ambient world, there's just light bouncing around, and that is some kind of function. Right? And so one way to understand what you're doing when you engineer these 3D displays is you're trying to reproduce some piece of that light field. Right? So for instance, when you have a 2-dimensional display, you're roughly trying to simulate the light field from a single perspective going through a single square. If you have a 3D display, maybe you now have 2 eyeballs who have slightly different light fields, right? Because they have different sources for their rays, and you want to get at least that piece right. Yeah? And so this is just one way to understand what goes wrong. Right? When, for example, you have like an occlusion conflict here. In other words, the bezel of the screen suddenly looks far away, the lily pad is close to your face, and your brain goes like, and it's less fun. Yeah? And in fact, these can create all kinds of crazy artifacts. So there's actually sort of a comfort zone that you typically have when you look at images. You don't like to cross your eyes, like look at something right in front of your face. But there's kind of an interesting issue here, which is if your computer screen physically is right in front of your face, even if you're trying to simulate something far away, your brain has to decide, well, do I focus on your computer screen as a 2-dimensional block of plastic sitting in front of my face, or do I try to convince myself that actually there's something sitting behind me, right? And if you don't get those depth cues just right, it might be ambiguous as to which one you choose, and that can create some conflict, right? And so oftentimes these displays will actually do things like, you can see here that there's quite some disparity between the 2 eyes, right? The red and the blue here. And maybe that's actually a bit of a problem for your display, because it's hard to focus on. So oftentimes people will do sort of a correction where, in fact, the 3D display looks farther than it really is in real life, because you're more willing to cope with that inaccuracy than to cope with the fact that like she should be right in front of your face, but your screen is here. and that's sort of problematic. There are all kinds of cool display technologies out there. So for example, auto stereoscopic displays would be one that look like 3D from exactly one perspective. Right? So a typical example, there's sort of two common classes of these things. One is to use these lenslets. Did you guys ever in elementary school get these bookmarks that have these things in them? Right? It's this little piece of plastic that kind of is bumpy like that. The idea is that the light comes from the back screen here, and then it refracts through this curved thing, and depending on the sort of angle, like the normal vector of this lenticular surface, the light is directed in a different way. Right? And so sitting behind the screen is probably a really weird looking image where there's a bunch of vertical stripes that all look like they're unrelated to one another. Right? That's because each of those stripes kind of gets bent off and sent in a different direction. Right? And so the idea is if you know exactly where your viewer is sitting, that's a problem. Right? Then you can kind of redirect the image toward their two eyes in just the right way if you're really careful about the calculation. Or if you do a lot of guessing to check and tell them it's right. These lenticular lenslets, or rather these parallel bearers are kind of similar, but here you're just controlling two directions instead of the whole segment. And these displays were popular for a little while. I mean, I feel like every once in a while they show up on cell phones and people just don't like them. They go away. So for example, there's this LG Optimus 3D phone. Any of you guys have one of these? I remember I saw one of them a couple years ago. Yeah, they really didn't last. People got excited that they're going to have 3D on their phone until they realized, like, well, you guys tell me, like, what are the drawbacks? Even if, for one thing, it's not clear that your phone needs to be 3D, like, that is a useful mode of interaction. But that aside, like, just from a display perspective, what are some drawbacks? Yeah. Battery life. The display is more complicated. We do 3D math. What else? Resolution is halved at best. Right? Because now you're sticking this big bumpy material in front of your screen, you're splitting all the pixels up between your two eyes, right? And so the resolution is much lower than it was before, and might be somewhat inaccurate, right? You're really relying on the fact that lenslet is sitting right on top of your screen in the proper way. So these haven't been terribly popular, I think possibly with the exception of this Nintendo 3DS, which sold okay. That makes sense because it's a 3D game. Okay. Of course, those displays are nice for a single viewer, but for other ones that may be less effective. Right? Like if you want to have a multi-view stereoscopic display that's unobtrusive, does all the things you might want for a 3D display. Of course, things become pretty complicated really fast. Right? So, for example, with these lenslet displays, you could do it. Right? You could just add more facets on that lenslet to kind of redirect light in all kinds of different ways. Again, the more of those that you add, the better sort of you're capturing this light field here. But of course, as we mentioned, the resolution gets worse because the spacing between each facet is sort of the limiting factor here. But there have been some examples of that over the years, right? So here's one of them was called a holographica, and it had different sort of views. One of them was actually proposed by Wojtek, one of the faculty here. Was developed at Mitsubishi Electric Research Laboratory.
People gain three-dimensional information from a variety of cues. Two of the most important ones are binocular parallax, seeing a different image with each eye, and motion parallax, seeing a different image when you move your head. We have built a display that provides both of these three-dimensional cues to multiple users without the use of glasses.
It's not so great, even relative to TVs at the time, which we thought it's because they are now. But
we have also built a complete 3D television system that allows for real-time acquisition, transmission, and display of dynamic three-dimensional scenes. All of the footage in this video shows live scenes that were simultaneously acquired, transmitted, and shown on a 3D display.
I'm actually not sure who that is. I bet it's somebody in the graphics. Right, but you can see that the actual acquisition and display is really not that complicated, right? You essentially are just simulating a capture the same way you're going to display it, but the resolution is limited. But there are many different techniques for doing these kinds of 3D displays. Here's another one that's kind of cool. It's going to load. Yeah, so here they have a mirror and they just have a fixed display, but the mirror is spinning. And if you synchronize them just right, you can simulate the light field that way, right? Because every time the mirror rotates, it's effectively reflecting light in a different direction. And that way you can walk all the way around the sky Has anybody ever seen one of these displays in practice? They're pretty cool. They have in museums sometimes. Yeah. And you actually can write software that controls these things. Why do you think these are terribly popular? I mean, they get pretty high resolution, all things considered. You can be interactive with them, and this is an old video. Like, why don't we see these all over the place? They're loud and dangerous, and they take up a lot of space. Yeah, there's literally a mirror spinning in there at like hundreds of tons per second, right? I mean, if your eye senses frames at 30 frames per second, that mirror's going to move awfully fast. So that like what you don't see is just a big spinning object, right? So you got to really want that 3D display in order to implement that technology. It's kind of cool. So for instance, you can capture the light field that gets reflected off of an object. That's a technology that people have, and you can simulate this little trinket sitting right behind it. Do a little photocopier. Okay. Right. And then finally, one more 3D display that people have tried over the years is just really one that simulates having a volume. In some sense, you can view what we just talked about as a simple version of that. Right? So we would call this a swept volume display. For exactly this reason, you are sweeping out the volume as you spin the screen around. These are actually really fun projects to try and do at home. They're not terribly challenging. You just have to find a motor that is pretty precise and doesn't like speed up and slow down a bunch. And synchronizing them is tricky, but if you have a good camera and a display, I think you can figure it out. Of course, as we say, these technologies are a problem because they're a big spinning object, and like if the wrong thing falls on your display, then it's just probably forever. There are volumetric displays that try to do simpler stuff. So for example, maybe you take one of these OLEDs or one of these displays that you can see through, and you just layer a bunch of them on top of each other. And this isn't quite, I wouldn't call this a 3D display. It's more like a 2.5D display, like a bunch of images kind of stacked together like slides. But you can get some notion of depth, which might be useful in certain places. So probably the most popular version of a 3D-ish display now are virtual reality and augmented reality tools. And of course we see these now, right? So I made these slides just, 2 years ago, and already they're a little out of date. But things like the Oculus VR, the HoloLens, and so on are all sort of the latest iteration of virtual reality devices that just put two basically screens in front of your eyes and simulate light field by a very tight loop between the display and sensing where you are and how you're moving. Right? And that's, of course, the main source of challenge in making VR display, right? Is that they have to keep up with these rapid motions that your eyes make and your head makes and so on. Or else, essentially, it feels like you're drunk, right? Like somehow you move your head, or it feels as like how I would imagine somebody might feel if they were drunk. Right? They move their head and then the display comes. Yeah. Right. Of course, there are many different applications, and I don't think it's too surprising. I think one that kind of came and went was in the kind of consumer side. Right? In particular, there's the Google Glass. It was very popular when I was a graduate student, and we really don't see it anymore. So it remains to be seen whether that will have a rebirth someday or not. Yeah? And of course, I think everybody gets inspired by these goofy sci-fi movies where you can just occlude your display altogether and somehow see the world. Virtual reality technology dates back much farther than computers, which maybe you don't realize. But the technology itself, goes back to Wheatstone and all these people who figured out that I could put two lenses in front of your eyes and two different images, and out comes a 3D display. These were not the most high frame rate displays as they go, but I suppose you could swap out the image if you had a really fast graduate student behind you. But then really the first major breakthrough in what we would all call virtual reality or augmented reality came with Ivan Sutherland. Anybody know the history, where he was from? 1960s? MIT, yeah. So the earliest VR technology really was here. I think at Lincoln Laboratory technically, but it was part of MIT. I always found this to be the most frightening looking photograph of an old experiment, but really it's pretty innocuous, right? It's just two displays in front of their eye, but something about that just looks like a church door. But anyway, roughly this technology is more or less what's going on in the modern displays now, right? I mean, it's just one display per eye, and some basic head tracking and so on. So this is sort of the history of augmented reality. the history of virtual reality is pretty similar. In fact, the earliest head-mounted display also dates back earlier than computer technology. I think it's really cute that it had a little point at the top just for fun. Like I feel like the modern patents now don't come with that little stylistic add-on. Certainly mine don't. And he had a good mustache. But that aside, the head-mounted display, I would say, relative to the analog virtual reality, is pretty similar. But then later on, there have been assorted attempts at doing HMDs and virtual reality since then. Nintendo had one all the way back in the 90s, which I think a lot of people forget. It was a total flop because the technology really wasn't there. But now, I think it kind of is, and we're slowly seeing people adopt this stuff. Right? So nowadays, there's this huge explosion of different technologies out there. And of course, the question is, like, okay, if we've known how to do it since, what, 1700, it's like, why did it take us so long? And of course, there are many different developments that really led to this technology in practice, right? So Ivan Sutherland's thing, what was the name of this little device he made? It was the Sword of Damocles, right? Was what he called it. Was one, and that was the idea that you can use digital technology to control this and to have a feedback loop rather than just a display, right? Which is the first step. Then later on in the 1980s and 90s, we thought a little more about human-computer interaction rather than just like computer interaction telling the human what to do, and discovered that really it takes two to make a technology like this. You have to understand the eye rather than just making a really cool display. And coming along with that came tools like haptics, right? Like, for example, gloves that maybe provided you additional feedback. And then what's come since then is the fact that, like, you know, what was probably a supercomputer in Sutherland's day is now some tiny fraction of the computing power that's sitting inside of your pocket. And so we can now do a computation at the latency that you would need to do rendering faster than your eye can process. A little frightening if you think about it. Like your phone is like smarter than your eye, and that's what we're leveraging to make these kinds of devices. But the kind of funny thing is really that this technology was all foreshadowed by this one piece of technology at MIT that included displays, rendering, head tracking, interaction, model generation. All of this stuff was impression. This photograph looks far less frightening, too. Right, but if you look at, for example, the Oculus DK2, you'll see it's exactly the same components, just a little bit of wireless and circuitry. So as you evaluate different technologies in this area, of course there are many different things to think about. One of the big ones is the field of view. Right, so remember the field of view is roughly what you can see through the AR, VR device. So for instance, here is the Oculus, and you can see the actual field of view is like a giant circle right ahead. And of course, what you really see in one of these displays, in this case, 110-degree angle. That's not so bad. 180 would be halfway. But all these different clones have different things behind them. Yep. One of the interesting ideas that Google had that I think was interesting but suffered from some PR issues, that the people that use the Google Glass were all kind of not very, well, they're great examples of the worst parts of Silicon Valley, and so this interesting technology kind of died with people's personality, in my opinion. But in any event, the Google Glass kind of went the opposite direction and said rather than occluding your eye with a fancy display and then trying to make the angle as big as possible, we're going to have a really small angle, but just have most of the light going into your eye actually just be from real life. Right? The idea being that, like, what do we all want to do? We just want to check our email faster, right? And if that's all we want to do, then we just have to beam text into your eye. And it doesn't matter if I can, like, see you people because I'm not paying attention to you anyway, right? Like, and so that was the basic philosophy behind Google Glass. And I don't think they were off the mark there. And indeed, did anybody actually get to try this before it died? Yeah, it's pretty cool. It works pretty well. And the technology looks something like this. So, you know, there's a display that's sitting on the side, and then there's a reflector that reflects the really bright light toward your eye, and otherwise you see right through it. One of the fun things about all these VR displays and AR displays is that the technology is just old optics, right? So in fact, if you've ever heard of Pepper's Ghost, you know, this funny illusion they use in theater sometimes. So like if I have a ghost in my theater production, I want the ghost to float. What I can do is take a piece of glass on top of, part of the stage. So like, here's the piece of glass. Here is the actor who's pretending to be a ghost, and he's standing off stage, right? And what happens is I shine a really bright light on the ghost, It's so bright that it gets reflected off of the piece of glass into the audience, but then everywhere else you can see through the glass to the scene behind. Right, so it looks like the ghost is floating. And that's exactly the illusion that's going on inside of your Google Glass, right? That there's this little piece of glass material where there's a really bright light showing your email, and that's what gets beamed into your brain, and the rest of what you see is just the scene behind you. Yeah. By the way, I included a link in the slides. There's a cute Lego how-to on how to make Cambridge ghost illusion. Let me see.
The ghost is located off to one side when it's out of view. The plexiglass is set at a 45-degree angle to both the audience and the ghost. At this angle, the background remains clearly visible, but the plexiglass also partially reflects an image of
So
the
you can
ghost.
see that there's actually glass.
To the audience, it looks like there's a transparent ghost in the scene in front of them. It's pretty simple. So now I'm going to show you some ways that you can implement this technique.
Oh,
The simplest way to apply it is in
They also show like a cute print can be put a scary face or a window to scare someone. And of course, the really cool stuff that happens now is that augmented realities aren't just like passively letting light go through your eye. The cycle in your cell phone is so fast that you can take in the signal from your camera, do processing, estimate the depth, place an object into the scene, and then render the whole thing together and display it in a way where your camera just looks like a window into the world. And that's what's enabling some really cool technologies. Like for instance, if any of you guys have played with the AR kit on some of these cell phones, like I think, I was just meeting with one of these companies, Wayfair, you know these guys that make furniture? And they actually have technology now where you can point your phone in like a corner of your room and say, I'm curious what this chair is going to look like here. And actually kind of look through your phone and walk around, and it looks like your bedroom just with the chair sitting there. And it's amazing. They can composite this stuff together fast enough, understand the lighting in your room, and track points well enough that it doesn't look like this chair is like floating in the air. It's a great kind of success of the computer vision and graphics world working together in harmony. So anyway, you can categorize these displays in all kinds of different ways. I don't think it's worth kind of dwelling on it. And what's important to know is that really it depends on what you care about, right? Whether you care about lots of resolution right in the center. Google Glass was purposefully offset a little bit because you want your email over here while you look at everything in front of you. I think it would legitimately be annoying if your email were right in front of you. At least we were Piazza, nothing personal. But there are all kinds of different axes you can use to display to understand these things. So anyway, the slides that I'll post online have all kinds of other material on how to compare these different things. I don't think it's worth going through all these specs. I think you guys get an idea. So maybe we'll call it for the day. In our next class, we'll hear about some research, hopefully some of which is related to today's topic. In particular, the Vortex group does a lot of hardware kind of stuff. And then I'm excited to hear about all of your projects, okay? So I'll see you all on Thursday. I really hope you guys do the courtesy to our guests of coming to the lecture and spend it on being a quiz. And I'll see you then. Okay.